In the previous lesson, we learned that pH is equal to the negative log of the concentration H+. And basically, that is because that letter P right there is equal to the negative log with a base of 10. And if I have POH, it will be negative log to the concentration of OH. In another term, when you have P of anything, it's basically the negative log to the concentration of that anything. Then we also learn how to write the equilibrium expression constant in terms of K. And basically it is the product over the reactants. And lastly, we also realize that in this unit we are looking at concentration in terms of molarity. And molarity is expressed in terms of M, or the letter M, and that is always equal to relative of 1 liter, and on top will be the number of moles. So these are the information that you need to know before we can solve a more complicated problems in this lesson. For example, we have lactic acid is 1.6% dissociated, or another term is ionized in water, okay, in a 0.5 molarity, and of course this is the lactic acid right there at 298 Kelvin. And in this case we have to write the Ka expression. Why is there a letter A? Because this is the dissociation constant of an acid right there. And calculate its values. Well, first of all, we have that right there. So we need to rewrite in a way that we can set up the ICE table. And of course, the ICE table will look like this. ICE, initial, change, and equilibrium. So for the initials of the lactic acid, if we go back to the problem, it's given to us that we have a 0.5 molarity. So of course this is your initial. So at the beginning of the chemical reaction, we have 0.5 molarity. And this 0.5 molar concentration of lactic acid will react with itself or dissociate in water to produce these 2 ions. And of course, because it's an acid, it's going to produce the H+. And at the beginning, or initially, we would have 0 of the product. Now let's look at the change. And this is expressed in terms of X relative to the coefficient. So we would have minus X. It is minus because the reactant are being used to make the product. In this case, of course the product would be plus X and then plus X. So some of the reactant in terms of X is being used up to make some of the product in terms of X. And these are represented by the coefficient. That's why they are 1. Okay? Now let's look at the equilibrium. Okay, so this reaction is actually reversible to some extent. So let's look at equilibrium. Well, equilibrium is what happened to the initial over time. In this case, we take the initial minus the change. In this case, it's plus. So 0 plus X, that gave us X. And 0 plus X, that just gave us X. Okay. Now, if we look at the ICE table, it looks like we don't have enough information to solve for X. But it is given to you hidden in the problem. And that is the percent of dissociated right there. What does that mean? The word dissociated or ionized. Basically, you initially have that certain amount of acid right there. And only 1.6% of that is dissociated or reacted into that ion. So that's where the hidden information is. In that case, isn't this just represent the changes in terms of 1.66% of the initial? If that's the case, all we have to do is take that initial of lactic acid that we have, which is 0.5, okay? And we just have to multiply that by the percent that's being disassociated. So multiply by 1.66%. But we never multiply the percent directly. We had to convert this to decimal. And that, of course, would give us 0.0166 in terms of decimal. So this is the decimal form of this percent. And of course this is being multiplied to that. And what do we have? 0.5 times 0.0166. And that gives us 8.3 times 10 to the negative 3. 8.3 times 10 to the negative 3. And of course this is actually represent the changes, right? Which in this case, it happened to be x. If this were to be a 2 right there, that would tell us it is 2x. Does that make sense? So be careful with that. Okay, keep that in mind. If this were to be a 2 right there, this would be 2x right there. So be careful with that. But in this case, it's just x. And once we have our x values, we can plug this in here, plug this in here, and plug this in here. Well, since this is our x already, so we just plug in directly. But this is where that we have to worry about. So I'm going to have this written right here. So to solve for this part, what do we have to do is 0.5 minus 8.3 times 10 to the negative 3. And that will give us a concentration for this part. And of course this is the EXP fund. Giving us 4.9 times 10 to the negative 1. And once we have that, we just plug into our equilibrium expression constant, which we know Ka is equal to H plus time the other product, or the lactate ions, divided by the reactant, which is the lactic acid right there. And then we just substitute this in terms of x, but we know those values already, so we just substitute in this directly. In this case, this is 8.33 times 10 to the negative 3. And then the other one, for this one, is also the same thing, 8.33 times 10 to the negative 3. And this, of course, expressed in terms of molar concentration divided by this on the bottom, which is right here. We just solved that. (4.9) times 10 to the negative 1. And if we plug this into a calculator, 8.3 exp minus 3, and of course they times each other, time 8.3 exp minus 3, and divided by the bottom part, 4.9 exp minus 1, give us 1.4 times 10 to the negative 4. 1.4 times 10 to the negative 4. And that is the values of our Ka right there. Now another question that can be asked from this problem is that calculate the pH of 0.5 molarity of the lactic acid. Well, first of all, we have this, don't we? And we know that if we have 0.5 molarity of acid right there, it will dissociate in 1.66% only. So only 1.66% will produce in terms of the H+. And this is where our pH is going to be. This is the concentration that we need to look for, which we just solve in terms of X, right? So isn't that nice? So all we have to do is take the negative log to the concentration of H+. Well, in this case, we know it is represented in terms of X. So in order to solve for the pH, we cannot just take this negative log of this directly, like this. Negative log of 0.5 molarity. This doesn't work because it doesn't disassociate. So we cannot just take a negative log of 0.5 of this lactic acid directly, because this is a weak acid. It doesn't disassociate completely. If it's a strong acid and we assume it's going to be 100% disassociation, then it will be fine, because this will give us 1-to-1 ratio, okay? But it is not. It's only disassociate in terms of what? It's only 1.66 is being ionized. And that's the reason why we have to solve for this X first. If we don't, we have to assume that this is a strong acid, but that's not true. This is a weak acid. And that's the reason why we couldn't take this negative log of this concentration directly. So what we have to do is we have to go back and look at what is happening at equilibrium in terms of the concentration of H. And that is our concentration right there. So to get the pH, we need to take the negative log of the concentration of H plus, that is dissociate at 1.66%, which in this case is equal to negative log of 8.3 times 10 to the negative 3. And that's the concentration that's happening at 1.6%. And what does that give us? Negative log 8.3 exp to the negative 3 give us 2.08, which we can round it up to 2.1, and that's equal to our pH with 1.6% dissociation. Because this is a weak acid. If it's a strong acid, then our life will be a lot easier, right? Because we just use that values right there, and boom, we're done. Because it's 100% dissociation for any strong acid. Another type of problem that we can get from this type of chemical reaction is this. We can calculate the pH of a solution form by dissolving 0.045 moles of solid sodium lactate. Okay, that's very important, okay, because it gives us the chemical formula of sodium lactate. And we know that this will dissolve and ionize into Na plus for that Na part. And of course this would be C3H5O3 minus. And this will be the ion that produced from sodium lactate in a 250 milliliters of 0.50 molarity of lactic acid, which we just observed before. Assume that the volume is negligible. So what is negligible? Think of the term neglect. When you neglect somebody, you ignore that person. So ignore it. Okay? Well, first of all, we need to realize that what have we learned about this reaction right here? Well, we just learned that the Ka that we just saw for right here is equal to 1.4 times 10 to the negative 4, okay? Well, in this case, under this condition, when it is 1.6% dissociated, we would have x equal to 8.3 to the negative 3x. But, is that what happened in this case? No. Basically, what happened is now we just dissolved 0.045 moles of solid lactate. So of course we know that this is broken down into these ions, that telling you that we are adding this component here. And that's what's going to change the initial. So we have to rewrite this and set up the ice table again. So again, we have to set up the ice table again and combine with our knowledge of the Ka that we just solved right here to solve for the new x. So just like the problem that we did before, where the K or the equilibrium is given, and then we have to solve for the x. But in this case, that equilibrium is being solved in the first part. So keep that in mind. That's what makes this problem so difficult, because they don't give us a K equilibrium at the very beginning in the question, but they break into part that we have to solve it first to now use that to solve for the x in this case. So let's rewrite this chemical reaction and set up our ice table. And of course the ice table will look like this. Now, we know that this right here is given to us. What is it? Well, in this case, it's telling us that we are starting with 250 or 250 millimeter of this 0.5 molarity. Well, remember molarity here has to be per liter, right? So we have to deal with this part first. How does that work? We have to convert this into liter, 1, 2, 3, and that will give us 0.25 liter. And what happens is that this 0.25 liter is the volume of this container. But what do they mean by the volume change is negligible? Well, that means to be ignored. They are referring to this volume of the solid right there. It is a small amount that when you add this in here, it wouldn't change that volumes. Okay, so keep that in mind. Very, very important. So let's go back and look at the ice table. Well, for lactic acid is easy for the initial. It would just be that, 0.5. Why don't we divide 0.5 by that? Well, that's because they give you in terms of molarity already. If they were given to if they were to give you in moles, then you would divide it by that volume to get your molarity. Okay, so that's the reason why. It's already tells us the concentration of lactic acid initially. And then from there, we realize that this lactic acid, just like we did before, right? It will disassociate to make that ions, and it's only 6% dissociation. And of course, right now, initially it would be 0. But now, this lactic acid is being reacted with the sodium lactate because they told you that they just dissolve it in here. How is that going to affect everything? So now this initial is no longer just 0 like we have over here. Okay, so we just basically rewrite this ice table, but in the new condition that they decide to add 0.045 mole into here. So this is no longer 0 anymore, but rather it is based on this moles being added initially to react with the lactic acid. And what makes it difficult is they give it in terms of mole, not in terms of concentration. So we have to take that mole and convert it to concentration, which is divided by the volume. And that's important because the volume, it doesn't need to be accounted with that mole there, right? So we just use that 0.25. And that will give us your molarity of the lactate ions that's producing from the sodium lactate. And let's plug that into a calculator. and give us 1.8 to the negative 1, which in decimal form is a lot easier to write. 0.18. So this is 0.18 molarity. And that is going to be right here. Now do you see how this problem has changed? Not because we are not just looking at the lactic acid dissolved into this two product, but they take this and they mix it with solid sodium lactate, which is producing the lactate ions as one of the product, and that changed your initial right away. And the rest for the ice table will just be the same. Of course, this would be minus x, this would be plus x, and this would be plus x. And then, of course, the equilibrium is going to change. We have 0.5 minus x. We have x right there, and we have 0.8 plus x right there. And again, we know that equilibrium constant doesn't change unless you change the temperature. And this has happened at the same temperature, which is 298 Kelvin. That means the Ka is going to be the same. And we just solve for that in the first part, which is right here. 1.4 times 10 to the negative 4. Okay, so that's what we have. Negative 4. So let's set up our Ka in terms of the formula, and we just plug in later, okay? So this is for that part right there, the product, and this is another product. Over the reactant. And now we just substitute in terms of x. So we have x times 0.18 minus x right there. Okay, this is for that part right there. And on the bottom will be 0.5 minus x. Okay? Just like the same problem we did before, where we are given the k and we have to solve for x. But in this case, we have to solve for the Ka, okay? Now let's rewrite this in terms of ignoring the middle part. 1.4 times 10 to the negative 4 equal to x times 0.18 minus x and 0.5 minus x. And if we look at this, we need to determine, can we ignore the x? So all we have to do is take one of this and compare it to our k. So we have 0.18 divided by your k, okay, or this Ka. If that is greater than 1000, that tells you that this Ka must be really, really small. So is that happening in this case? We have 0.8 divided by 1.4 exp minus 4. That gives us 1.8 times 10 to the third, which is equal to 1,800. And that is greater than 1,000. Whew! That was lucky. So what does that mean? We can now ignore that x. So if we ignore that x right there, we can also ignore that x right there as well. Beautiful. So as long as one of them proof in this rule, we can apply that to there. If we ignore the x, don't we just have x times 0.18 divided by 0.5? And if that's the case, that's pretty easy. All we had to do is bring that 5 over there. So that way, we have multiplied by 0.5, and we can just ignore that part. So we have 0.5 times the Ka, which is 1.4 times 10 to the negative 4, equal to x times 0.18. And now we can solve for that easily. 0.5 times 0.5 times 1.4 exp minus 4 equal to 7.0 times 10 to the negative 5, and this side is 0.18x, and we just divided that by 0.18 on both sides, which is equal to x, and that turned out to be 3.89 times 10 to the negative 4th power. And now we have to find our pH. And our pH is negative log of the concentration of H+. And this is what we are looking for. Well, it's expressed in terms of X, which we just found right there. So all we have to do is take the negative log of this, and that will give us our pH. So of course pH is equal to negative log of the concentration of H, which is represented by X at equilibrium, which is equal to that right there. So we have log of 3.89 times 10 to the negative 4. And what would that give us? And that gives us 3.41 as our pH. So that is the answer right there.